Alrighty, welcome to 2D kinematics. The good thing about 2D kinematics is that all of our relationships between position, velocity, and acceleration are the same. So in that way, there aren't any new concepts about new terms or how they are connected. But now everything is going to be in two dimensions. So our position will be a vector that has an x component and a y component. Velocity also will be a vector with x and y component. Acceleration will be a vector that has x and y components as well. Yeah, and so the math winds up being a little more complicated, and that does introduce a new level of complexity to some of the conceptual relationships as well. If we have an object thrown straight up, then the question is, what's the x component of its velocity? Well, if it's thrown straight up, we know that its velocity, well, usually we call the y direction up and the x direction horizontally. And therefore, this velocity, if it's thrown straight up, is going to be 0, comma something. Okay. The acceleration of an object that's thrown, we know is just because of gravity. So as long as we're on Earth, we can say that the x component of our acceleration is 0, because we know the acceleration is straight down. Okay. What if it was thrown straight down? Well, the x component of its velocity is still 0. The x component of its acceleration is still 0. So the change in the y component, this would be v naught up, this would be v naught down, doesn't have any effect on those x components. Let's say if we have a constant velocity, 3 meters per second, 4 meters per second, with the x direction being east-west, the y direction being north-south. So 3 meters per second east, 4 meters per second north. How far east does the object travel in 2 seconds? Well, going constant velocity, it's going at 3 meters per second east, 2 seconds, so it goes 6 meters. The velocity was instead this. The question is, how far east does the object travel? It is exactly the same. So the point that I'm making here is that whatever is going on with one component of motion doesn't affect what's happening with the other component. So changing the north-south velocity had no effect on what was going on in the east-west direction. Changing the up-down velocity has no effect on what's going on in the horizontal direction. So perpendicular components of motion are independent. So an acceleration in the y direction, velocity in the y direction, doesn't have any effect on the x direction motion. Because of that, we can write all of our kinematic equations kind of separately. So we have the acceleration equation. To find the x component of acceleration, we find the change in velocity in the x direction over time. To find the y component of acceleration, we do the same thing, but in the delta v subscript y, delta y over x would be average velocity. Okay. And any of our equations we can write, any of our kinematic equations we can write out with subscripts, again, as long as we have constant acceleration. These are the equations for constant acceleration. Etc. The time-dependent equation is one that we'll use frequently, so I will go ahead and write that in each direction. Yep. And we can also write the time-independent equation. And actually, that's the only one left, so I'll go ahead and write it. So the components of motion are independent. We only have to deal with x components if we're finding out something about the x direction. We can only have to deal with y components if we're finding out something about the y direction. The linking factor between the two directions is time, because time is a scalar, and it shows up in all of our directions. Projectile motion is when an object is flying through the air, and this is an example of free fall. On Earth, the acceleration of a projectile, if we neglect air resistance, is going to be 0 in the horizontal direction and 9.8 meters per second squared downward in the vertical direction if we're calling up positive. Up the positive y direction. So this changes our equation set fairly dramatically. If we look in the x direction, acceleration is 0, so this equation becomes 0 equals 0. Acceleration is 0, so this equation just becomes delta x equals v naught t. If acceleration is 0, these two, v naught and v final, are going to be the same thing, so this also becomes v naught t. And this one becomes 0 equals 0. So having 0 acceleration in the horizontal direction means that in the x direction for projectile motion, we're only ever going to use that. Okay. In the y direction, we still have our normal. Our acceleration in the y direction is 9.8 meters per second squared downward, so I'll call that negative g. So apart from that, we'll still have all the same equations in the y direction. In practice, we don't usually use whose equation is it? I forget whose equation it is in your class. We don't usually use this guy when we're dealing with projectile motion because we always know the acceleration. So it doesn't make sense to use the equation that doesn't have acceleration. So time, as I said, is the link between the components of motion. A lot of times, well, often we will solve for time in one equation, plug it into the other one, plug it into the other component. So here's a question. If I fire a bullet horizontally, at the same time drop a bullet from the same height, which will hit the ground first? Well, if I fire a bullet from a gun horizontally, the y component of its velocity is 0 initially. The one that I drop, the y component of its velocity is 0. And the vertical displacement each is traveling through is the same. They're going from the same height to the ground. So which will hit the ground first? Well, they'll hit the ground at the same time because they have the same initial velocity in the y direction, same delta y, and of course they have the same acceleration. Therefore, it takes the same amount of time to hit the ground. The horizontal component of the motion doesn't matter for the answer to this question, because this question is only about the vertical component of motion. Okay. And I'll demonstrate that this is true with our marble launcher when you see me in class. Here's another question. Throw one ball straight up, another up and forward, so they reach the same maximum height. Okay. So one's just going straight up, woo, and we get up to here, we go straight back down. Whereas another is going like this. Okay. They do reach the same maximum height. Okay. Well, if they reach the same maximum height, obviously, which quantities are the same? Well, our maximum height, duh, is the same. But to reach the same maximum, well, we know acceleration is the same. And to reach the same maximum height, that means that we must have the same y component of initial velocity. Also, the time it takes to reach a given height will be the same. All be at the same height at the same time. And what's different? Well, basically, the horizontal component of motion. X component of velocity, delta x, acceleration in the x direction is the same. Yeah, but the horizontal components of motion are different. But in the vertical direction, they're doing exactly the same.